Hello, welcome to Algebra 1 with Miss Betsy. This is part 2 of a 3-part teaching on how to solve interest problems using two variables. As my text, I'm using Algebra 1 for Christian Schools. It's published by Bob Jones University Press. I'm in the second edition, section 7.8, beginning on page 304. You don't have to be using that text to be able to gain something from this video. However, this second part right now, I'm going through the second example, which begins on page 305, continuing on to page 306. Before I get started, did you hear about the guy who fell off a 100-foot ladder and he didn't get hurt? Well, he didn't get hurt because he fell off the first rung of that 100-foot ladder. So, as you'll remember, we know that there's a very important equation. It's one that we use to calculate simple interest, and it's principal times rate times time is equal to interest. Principal, of course, is the amount of money that's invested. The rate is the decimal representation of the percentage. So 8% interest would be represented by 0.08 or 8/100ths. The time is the time that the financial institution has that money and is borrowing that money, and it's the time in years. 1 year or annual interest would be represented by 1. 6 months interest would be 0.5. 3 months interest would be 0.25. 5 months interest would be 5 divided by 12, because you have 5 out of 12 months in the year for which you are gaining interest. You can see that I already have this set up where we see that we're going to have an amount of money that's been invested at 11%, an amount of money that's invested at 9%. So let's go ahead and look at page 305 and read our problem. The 6-month interest check from an 11% investment was $95 more than a 6-month interest check from a 9% investment. If $5,000 was invested, how much was invested at each rate? A pretty standard question that we're being asked to solve. How much money is invested at each rate? So let's have X represent the amount of money at 11%, the amount invested at 11%, and Y would be the amount invested then at 9%. Okay? What else do we have? Well, we're going to have to fill in our table, aren't we? Easy to begin with. The principal that we're investing, we don't know what it is, but we do know that the amount invested at 11%, we're going to use the variable X to represent that. The amount invested at 9%, we use the variable Y. What's the rate? Well, that's pretty easy. It's 11%. 0.11. Make certain that you use the correct decimal representation of the interest. 9/100ths, 9%. 11/100ths, 11%. What if you had 9.5% interest? 0.095. Make sure that you're converting percents to decimals properly. How long is this money invested? Our problem tells us that it is invested for 6 months. Well, it doesn't say that. Well, yeah, it does. It says that the 6-month interest check. In order to get an interest check for 6 months, your money has to be invested for 6 months. 6 months is 6/12ths of a year, or 0.5. 0.5. Interest is equal to principal times rate times time. So we have 0.11 times 0.5 times X. We're going to go ahead and make sure that we multiply 0.11 times 0.5. That's 55. But where does the decimal point go? How many decimal places do we have? 1, 2, 3. So our answer here to this product, 0.055 Don't make the mistake of saying 0.55x because 5 times 11 is 55. You have to count your decimal places. 1, 2, 3, 1, 2, 3. 0.09 times 0.5 times y is 0.045y. There's not much difficulty involved in filling out our chart here. You know your principal, use your x and y, do your multiplication, and we now have representations for principal and rate and time and interest for both sums of money, for both amounts of money. Now what we do, we go back to the book and see what equations we can create. It says $5,000 was invested. Oh boy, do we love those. $5,000 is invested. So the amount invested at $11,000 plus the amount invested at $9,000 plus the amount invested at $9,000. Hear my tongue getting all twisted up? The amount invested at 11% X dollars plus the amount invested at 9%, which is Y dollars, is equal to the total amount of money invested, which is $5,000. Now, look at your book and we have to come up with another equation. And you see that what they're talking about is they're comparing the 6-month interest checks. We don't even have to worry about the fact that what percentage it is. We're just going to compare the checks. Now let me write my seesaw here. This little triangle here, that's the point, the balance point for my seesaw. And if we have on this left-hand side, this is the 11% check. And on this right-hand side, I have the 9% check. Now, why do I have my equation, my seesaw, out of balance? Because if you have money invested for the same amount of time, the check where the interest rate is bigger is going to be heavier. There's going to be more to it. So our equation is out of balance. We can't directly compare the 11% check and the 9%, can we? Because they're not equal. So we're going to have to see what we can do with these two expressions so that they are balanced, so that we can come up with an equation that's equal that we can use to solve for our unknown quantities. So let's go back and take another look and see what our text tells us. It says, this investment check here, the $11,000, the 11% investment check, was $95 more than the 9% check. So there's, think about it as pounds, there's 95 pounds more over here, or $95 more over here than there on this side. What are we going to have to do to bring this equation back in balance? Yep, that's exactly what we do. We have our 11% check. That's our 9% check plus $95. Now we have an equation that is balanced. Go ahead and look at these pictures here and make sure that you understand what I'm talking about here, because this type of balancing act you do in all sorts of different problems. You have a comparison given to, you can look and come up with an unequal comparison. Okay, interest check, interest check. They're different rates, so they're out of balance. How are they out of balance? Sometimes sketch yourself a little picture that says, okay, my 11% check is bigger, so I'm either going to take something away from this left-hand side to balance it, or I'm going to add something to the right-hand side. We add the difference here of $95, and our equation, or our seesaw here, if you will, is now balanced. So, what can we do to write an equation, an algebraic equation that describes that picture right there? Well, do we have an expression for the interest check from the amount invested of 11%? Sure we do. Here's the interest that is received. So we have 0.055x. That's the amount of interest earned on the quantity, on the principal that is deposited, thank you, at 11%. And that's equal to the 9% interest, 0.045y plus $95. Now we have two equations that we're going to manipulate so that we're able to come up with the amount of money invested at 9,000 at 9% and the amount of money invested at 11%. Now, I'm going to go ahead and think ahead a little bit. What do I want to do to solve this equation? What approach might I want to take? Well, substitution jumps out at me instead of trying to do some sort of multiplication where we eliminate the x's or we eliminate the y's. We can easily solve this first equation for y, can't we? If you subtract an x from both sides of the equation, you have y is equal to 5,000 minus x. And then we have a value that we can substitute in here for this y in this second equation, and we can go ahead and solve for x. However, this is complicated by the fact that we have a decimal number here. We want to clear this equation, the second equation of decimals. So we have only whole numbers in front of our variables. We only want whole number coefficients. What do I have to multiply by to eliminate the decimals? You multiply by the power of 10, 1, 2, 3 decimal places. You multiply by 10 to the third, which is 1,000. So we're going to multiply the left-hand side of the equation by 1,000. And we're going to multiply the right-hand side of the equation by 1,000. And that will clear this equation of decimals, which means that it removes the decimals, makes our computation more straightforward. 1,000 times this, we end up with 55x is equal to, do you see what I have here? This is the distributive property. 1,000 times 95, 1,000 times 0.045. 55x is equal to 45y plus 95,000. Use your scratch paper and verify that. 45y, 55x. Now we can substitute the y value of 5,000 minus x. Let me see if I'm still tracking with your book. Okay. 55x is equal to 45 times, I'm going to substitute in here in blue, 5,000 minus x plus 95,000. All I did was substitute 5,000 minus x. Do my multiplication. 55x is equal to 45 times 5 is 225,000. 225, not 222, 225,000 minus 45x plus 95,000. Let me make sure that I've got my multiplication correct. And I do. We want to have our x on the left-hand side of the equation. We do that by adding 45x to both sides of the equation. Gives us 100x is equal to 225,000 plus 95,000. 100x is equal to 320,000. See, these numbers get really, really big, but when you are, the only reason they're big like this is because we multiplied by a power of 10 to eliminate these decimals, to convert these numbers here into something that is whole numbers only. What are we going to do now? We're going to divide both sides of this equation by 100. X is equal to $3,200. What is X? It's the amount of money that's invested at 11%. What is Y equal to? Y is the amount of money invested at 9%. Right here, this tells us that Y is equal to 5,000 minus X. 5,000 minus 3,200. So Y is equal to $1,800, $1,800 invested at 9%. And there you have the solution to this second example, the end of part 2. I have one more problem to do, one more video that will illustrate to you, be an example for you of how to solve these interest problems. I'll be right back.